Hello everyone and welcome to our discussion of Chapter 8, which centers on relational algebra and relational calculus. Jumping straight in, Chapter 8 talks about relational algebra in section 8.1 and then relational calculus in 8.2, and we'll cover both of those pretty extensively. So jumping straight into what is relational algebra. And relational algebra is the basic set of operations for the relational model. The operations enable a user to specify basic retrieval requests or queries. The results of an operation is a new relation, which may have been formed from one or more input relations. This property makes the algebra closed. All objects in relational algebra are relations. So there's nothing else other than relational objects inside of the space or relational entities. The algebra operations thus produce new relations. These can be further manipulated using operations of the same algebra. A sequence of relational algebra operations form a relational algebra expression. The result of a relational algebra expression is also a relation that represents the results of a database query or retrieval request. A brief history of the origins of algebra. And basically, a book was written back in Morocco that dealt with arithmetic of variables. The book was translated into Latin. Its title gave algebra its name. The variables were called shay. Shay is Arabic for thing. The Spanish translations of shay as exe, and in this time, this word was abbreviated as X, so which is where you get your X from. Where does the word algorithm come from? Algorithm comes from al-Khwarizmi, and this is a reference here to the history of algebra. So relational algebra consists of several groups of operations. Urinary relational operations include select, project, and rename with the corresponding symbols, sigma, pi, and rho. Relational algebra operations come from set theory, or some of them do. In this case, things like union, the difference, or minus, intersection, and Cartesian products are all from set theory. So essentially, you've got your union where you're unioning two things together. You got an intersection where you're looking for the things that are common to both and the differences, which are things which are not in both. Binary relational operations include things like joins. Several variations of join exist. There's left, right, equijoin, inner join, and so on. Divisions as well. Relational algebra overview continued. Additional relational operators and operations include things like outer joins, outer unions, aggregate functions. These compute a summary of information, for example, things like sum, count, average, min, and max. Database state for a company. All examples discussed below refer to the company database shown here. This is coming back from chapter 5.7 or section 5.7, which we've discussed previously. When we talk about urinary set operations, we start off typically with select. It is probably the most common. The select operation, denoted by sigma, is used to select a subset of tuples from a relation based on a selection condition. The selection condition acts as a filter. It keeps only those tuples that satisfy the qualifying condition. Tuples satisfying this condition are selected, whereas other tuples are discarded, filtered out. For example, select the employee tuples whose department number is 4. So you have sigma DNO equals 4 of employee, and select the employees tuples whose salary are greater than 30,000. So a sigma salary greater than 30,000 on employee. In general, the select operation is denoted by the sigma with some relation and condition. So the sigma is used to denote the select operator. The selection condition is a Boolean condition expression specified on the attributes of relation R. Tuples that make up the condition the condition true are selected and appear in the results of the operation, whereas tuples that make the condition false are filtered out and it is discarded from the results of the operation. Continuing our discussion of select, the select operation properties. Select operation produces a set relation S that has the same schema or attributes as R. Select sigma is commutative, so the ordering of them, nesting of them is going to be roughly the same because of the commutative property. A cascade or sequence of select operations may be applied in any order. A cascade of select operations may be replaced by a single selection with conjunction of all of the conditions. Selection of condition 1, condition 2, condition 3 is the same as condition 2 and condition 1 and condition 2 and condition 3 on that same relation. The number of tuples in the results of the select is less than or equal to the number of tuples in the input relation R. So it's going to be at most the same as is in there initially, but likely will be less depending upon the conditions. The following query results refer to the database state that we also discussed back in figure 5.6. Urinary relational operations projection is denoted by pi. This operation keeps certain columns attributes from relation and discards the other columns. A project creates a vertical partitioning. The list of specified columns attributes is kept in each tuple, and other attributes in each tuple are discarded. For example, to list the employee's first name and last name and salary, the following is used, and it is pi L name, F name, salary on employee. The general form of that projection is as follows. Pi and then the attribute list on R. So pi is the symbol used to represent the projection operation. The attribute list is the desired list of attributes from relation R. The project operation removes any duplicate tuples. This is because the results of projection operation must be a set of tuples. Mathematical sets do not allow duplicate elements. And this is slightly different than what you'll see in the actual database operations because duplicates aren't necessarily eliminated there unless you use the word distinct. Project operation properties, the number of tuples in the set of projection. So the list is always less or equal to the number of tuples in R. If the list of attributes includes a key of R, then the number of tuples in the result of the project is equal to the number of tuples in R. Project is not cumulative, so the order will matter. So keep that in mind. Examples of applying select and project operations. So we're selecting projecting the DNO equals 4 and salary and is greater than 2,500, or it's 5 and salary is greater than 30,000 on employee. That's one example. The second is the selection where we're selecting first name, last name, and salary on employees, and then sex and salary off of employee. Relational algebra expressions. We may want to apply several relational algebra operations, one after the other. Either we can write the operations as a single relational algebra expression by nesting the operations, or we can apply one operation at a time and create an intermediate result relation. In the latter case, we must give names to the relations that hold the intermediate results. This is kind of similar to using like a temp table. So to retrieve the first, last name, and salary of all employees who work in the department number 5, we must apply a select and a project operation. We can write a single relational algebra expression as follows. Selecting basically pi, first name, last name, salary, selecting where it is DNO equal to 5 on employee. Or we can explicitly show the sequence of operations by giving a name to each intermediate relation. So dep5 imps takes on the value from essentially the selection or the projection where the selection where the DNO is equal to 5. And then we select only those columns that we're interested in, first name, last name, and salary from dep5 imps, producing a result set. The rename operator is denoted by row. In some cases, we may want to rename attributes of a relation or the relation name or both. Useful when a query requires multiple operations necessary in some cases, such as a join, which we'll talk about later. The general rename operation is as follows, and basically it changes the name, it changes both the relation name to S, and the column attributes are renamed to P sub S. The relationship name is only changed to S in this example, and then the column attribute names is only in the final example. For convenience, we also use a shorthand for renaming attributes in an intermediate relation. If we write results takes on first name, last name, salary 5, the results will have the same attribute names as dep 5, the same attributes as employee. However, if we write it as result and then list the attributes, we're essentially renaming them during the creation of that new relation, and all 10 of those characteristics. Note that the arrow symbol is an assignment operator, so it's basically taking on the value or assigns to. An example of applying multiple operations using rename is on the screen. The union operation is essentially a binary operator denoted by the union sign. The results of R union S is a relation that includes all the tuples that are in either R or S or both. Duplicate tuples are eliminated. The two operands relations R and S must be type compatible or for the union operation to work, or they must be union compatible. R and S must have the same number of attributes. Each pair of corresponding attributes must be type compatible, the same or comparable domains. For example, to retrieve the Social Security number of all employees who work either in Department 5, result 1 below, or directly supervise an employee who works in Department 5, result 2 below, you can use the union operator as follows. The union operator produces the tuples that are in either result 1 or result 2 or both. And here is a visual representation of that as well. Relational algebra operations from set theory. Type compatibility of operands is required for the binary set operations union, also for intersection and set difference. R1, A1 through N, and R2, B1 through N are compatible if they have the same number of attributes and the domain of corresponding attributes are type compatible. The resulting relation for R union R1 union R2 also for intersection and negation is in the next slides. Here's the intersection denoted by intersection. The result of the operation R intersection S is a relation that includes all tuples that are in both R and S. The attribute names of the results will be the same as the attributes in R. The two operands R and S must be type compatible. Set difference is also a minus, or except is denoted by the minus sign. The results of R minus S is a relation that includes all the tuples that are in R but not in S. Here's a visual representation of that as well. Notice that both the union and intersections are commutative operations, that is R union S, S union R, and R intersect S is equal to S intersect R. Both union and intersection can be treated as in-area operations applicable to any number of relations, as both are associative operations. The minus operator is not commutative, that is in general. The Cartesian or cross-product operation. This operation is used to combine tuples of two relations in a combinatory fashion. It's denoted by R sub A1 through N and S sub B1 through M. It results in Q sub A1, A2, AN, B1, B2, BN in that order. The resulting relation state has one tuple for each combination of tuples, one from R and one from S. Hence, R has n to the R tuples denoted as follows, and S has n to the S tuples. The result will have R times S, which is basically the summation of the number of rows multiplied together. The two operands are not to have, do not have to have type compatibility. Generally, cross-product is not a meaningful operation, can become meaningful when applied with other operations such as filtering. To keep only combinations where dependence is related to the employee, we can add a select operation as follows. The result will now contain the name of female employees and their dependents. Figure 8.5 is a demonstration of a Cartesian product. The join operation is the sequence of Cartesian products followed by select is used quite commonly to identify and select related tuples from two relations. A special operation called a join combines the sequence into a single operation. This operation is very important for any relational database with more than a single relation because it allows us to combine related tuples from various relations. The general form of a join operation on two relations is as follows, where S and R can be relations that result from general relational algebra expressions. So the takeaway there is that join is so common that the combination of a Cartesian product with a condition is important enough to have its own thing. Binary operations, relational operations join. Suppose that we want to retrieve the name of the manager of each department. To get the manager's name, we need to combine the department tuple with the employee tuple whose SSN matches the manager's SSN value in the department tuple. We do this by using the join operator, and we basically say the department manager takes on the value of department joined with employee on manager SSN equals to SSN. Manager SSN equals SSN is the join condition, combines each department record with employee who manages the department. The join condition can also be specified as department dot manager SSN equals employee dot SSN, which is probably a little bit more expressive and perhaps more valid. Figure 8.6 is a result of the join operator. Some properties of join. The result of a relational relation Q with M plus N attributes is as follows. The result relation states that a state has one tuple for each combination of tuples, R from R, S from S, but only if they satisfy the join condition. Hence, R has N sub R tuples and S has N sub S tuples, where the join results will generally have less than R times S tuples, basically. So it's going to typically be a subset of the Cartesian product. Only related tuples based on the join condition will appear in the results. The general case of join operation is called a theta join. The join condition is called theta. Theta can be any general Boolean expression on the attributes of R and S, for example, and you get less than or equal or less than. Most join conditions involve one or more equality conditions ANDed together. For example, R dot A sub I is less than S dot B sub J, and some additional, perhaps nested conditions. Equijoin operations, the most commonly used of a join involves joining conditions with equality comparisons only. Such a join where the only comparison operation utilized is equal is commonly called an equijoin. The results of an equijoin will always have one or more pairs of attributes whose names need not be identical that have identical values in every tuple. The join seen in the previous example was an equijoin. Natural join operation is another variation of a join called a natural join. It's denoted by a star. Was created to get rid of the second Suplurius addition attribute of an equijoin condition because one of the pairs of the attribute with identical values is Suplurius. Superfluous, which basically means that you don't need both sides of the equality. The standard definition of a natural join requires that the two join attributes or pair of corresponding join attributes have the same name in both relations. If this is not the case, a renaming operation will be applied first. So what this is saying is that an example, to apply a natural join to denumber attributes of department and department locations, it is sufficient to write dep blocks takes on the value of department times dep locations. Only attributes with the same name is denumber. An implicit join condition is created based upon this attribute. The department.denumber equals department location.denumber. Another example is as follows. The implicit join condition includes each pair of attributes with the same name ANDed together. R.C equals S.C and R.D equals S.D. The results keep only one attribute of each pair. An example of the natural join operation. The set of operations including select, project, union, difference, rename, and Cartesian product. X is called a complete set because any other relational algebra expressions can be expressed by a combination of these 5 operations. Division operation. The division operation is applied to 2 relations, R sub z divided by S sub x, where x is a subset of z. T is equal to z minus x, and hence z equals x union y. That is, y be the set of attributes in R that are not attributes of S. The result of a division is a relation T sub y that includes a tuple T if tuples T sub R appears in R with T sub R sub y equals T, and with T sub R sub x equals T sub s for every tuple T sub s in S. For a tuple T to appear the result of T of the division, the values T must appear in R in combination with every tuple in S. And figure 8.8 is a visual representation of the division. Table 8.1 is a comparison of the operations of relational algebra: select, project, theta join, equijoin, natural join, union, intersection, difference, and Cartesian product, and division. Query tree notation. A query tree is an internal data structure to represent a query. The standard technique for eliminating the work involved in execution, the query, the generation of intermediate results, and optimization of the execution. Nodes stand for operations like select, project, join, rename, division. Leaf nodes represent base relations. A tree gives a good visual feel for the complexity of the query and the operations involved. Algebraic query optimization consists of rewriting the queries or modifying the query tree in into an equivalent tree. We'll talk about that in chapter 15. Here's an example of a query tree of an expression. Additional relational operations, aggregate functions and grouping. A type of request that cannot be expressed in the basic relational algebra is to specify mathematical aggregation functions on collections of values from the database. Examples of such functions include retrieving the average or total salary of an employee or the total number of employee tuples. These functions are used in simple statistical queries to summarize information from the database tuples. Common functions applied to collections of numeric values include sum, average, max, and min. The count function is used for counting tuples or values. Continuing our discussion of aggregate function operations, this is an example of min, max, sum, and count of a particular attribute on employee. Note count just counts the number of rows without removing duplicates. Using grouping with aggregates, the previous example all summarized one or more attributes of a set of tuples. Max salary or count, number of SSN. Grouping can be combined with aggregate functions. For example, for each department, retrieve the DNO, count, SSN, and average salary. A variation of aggregate functions F allows this grouping attributes placed on the left of the symbol, aggregate functions to the right. The above operation groups employees by DNO, department number, and computes the count of employees and average salary per department. Figure 8.10 is an aggregate function operation. Figure 7.1 is an example of a group by and a halving clause. Additional relational operations, recursive closure operations, another type of operation that is in general cannot be specified in the basic original relational algebra, is recursive closure. This operation is applied to a recursive relationship. An example of a recursive operation is to retrieve all the supervisees of an employee E at all levels, that is, all the employees E's directly supervised by E, all employees E's double prime directly supervised, and so on. Although it is possible to retrieve the employees at each level and then take their union, we cannot in general satisfy a query such as retrieve the supervisees of James Borg at all levels without utilizing a looping mechanism. SQL3 standardized includes syntax for recursive closure. A figure 811 that shows two-level recursive query. Outer join operation. In natural join and equijoin tuples without a matching or related tuple are eliminated from the join results. Tuple with null in the join attributes are also eliminated. This amounts to loss of information. A set of operations called outer joins can be used where we want to keep all of the tuples in R, or all those in S, or all those in both relations in the result of the join, regardless of whether they are not, they have a matching tuple in the relation. Left outer joins operations keep every tuple in the first or left relation R in R S. If no matching tuple is found in S, then the attributes in S in the join results are filtered or padded with null values. A similar operation, right outer join, keeps the tuple, every tuple in the second or right relation S of the result RS. A third operation, full outer join, is denoted by that symbol, keeps all tuples in both left and right relations where no matching tuple can be found, padding them with nulls as needed. Figure 812, the results of a left outer join operation. Outer union operations. The outer union operation was developed to take the union of tuples from two relations if the relations are not type compatible. This operation will take the union of tuples from in two relations, R sub xy and S sub xz, that are partially compatible, meaning that only some of the attributes, say x, are type compatible. The attributes that are type compatible are represented only once in the result and are thus those attributes that are not type compatible for either relation are also kept in the result relation. An example of an outer union can be applied to two relations whose schemas are student, name, SSN, department, and advisor, and instructor, name, SSN, department, and rank. Tuples from the two relations are matched based upon having the same combination of values of the shared attributes, name, SSN, and department. If a student is also an instructor, both advisor and rank will have a value. Otherwise, one of those two attributes will be null. The result relation student or instructor will have the following attributes. Example of queries in relational algebra, procedural form. Q sub 1, retrieve the name and addresses of all employees who work for the research department. Q6, retrieve all the names of employees who have no dependents. As a single expression, these queries become Q1, retrieve the names and addresses of all employees who work for the research department, and Q6, retrieve the names of employees who have no dependents. A relational calculus expression creates a new relation which is specified in terms of variables that range over rows of the stored database relations. In tuple calculus, or over columns of the stored relations in domain calculus. In a calculus expression, there is no order of operations to specify how to retrieve the query results. A calculus expression specifies only what information the result should contain. This is the main distinguishing feature between relational algebra and relational calculus. Relational calculus is considered to be a non-procedural or declarative language. This differs from relational algebra, where we must write a sequence of operations to specify a retrieval request. Hence, relational algebra can be considered as a procedural way of stating a query. The tuple relational calculus is based on specifying a number of tuple variables. Each tuple variable usually ranges over a particular database relation, meaning that the variable may take as its value any individual tuple from that relation. A simple tuple relational calculus query is of the form where T is a tuple variable and condition T is a conditional expression involving T. The results of such a query is that the set of all tuples that satisfy condition T. An example, to find the first and last names of all employees whose salaries are above 50,000, we can write the following tuple calculus expression, t.fname.lname given employee sub t and t sub salary is greater than 50,000. The condition employee t sub t specifies that the range relation of tuple variable t is employee, the first and last name from the projection protecting first name last name of each employee tuple t that satisfies the condition will be retrieved. Two special symbols called quantifiers can appear in formulas. They are universal quantifiers and existential qualifiers. Informally, a tuple variable t is bound if it is a qualified or quantified, meaning that it appears in a existence or universal quantifier or an existence qualifier. Otherwise, it is free. If f is a formula, then so are where t is a tuple variable. The formula is true if the formula f evaluates to true for some or at least one tuple assigned to free occurrences in T in F, otherwise is false. The formula is true if the formula F evaluates to true for every tuple in the universe assigned to free occurrences of T in F, otherwise it is false. Is called the universal or for all qualifier because every tuple in the universe of tuples must make F true to make the quantified formula true. Existence is called existential or there exist qualifier because any tuple that exists in the universe of tuples may make F true to make the quantified formula true. Retrieve the name and addresses of all the employees who work for the research department. The query can be expressed as the only free tuple variables in a relational calculus expression should be those that appear on the left of the bar. In the above query, T is the only free variable. It is then bound successfully to each tuple. If a tuple satisfies the conditions specified in the query, the attributes fname and lname and address are retrieved for each tuple. The condition employee T and department D specifies the range relations for T and D. The condition D.dname equals research is a select condition and corresponds to a select operation in the relational algebra, whereas the condition D.dnumber and T.dno is a join condition. Find the names of employees who work in all the projects controlled by department number 5. The query can be as follows. Exclude from the universe qualifiers all tuples that are not interested in by making the condition true for all such tuples. The first tuples to exclude by making them evaluate automatically to true are those that are not in the relation R of interest. In the above query, using the expression not project of X inside of the universal quantifier formula evaluates to true for all tuples X that are not in the project relation. Then we exclude the tuples who are not interested in from R itself. The expression not X equal D num equals 5 evaluates to true for all tuples X that are in the project relation but not controlled by department 5. Finally, we specified a condition that must hold true for all remaining tuples. The language SQL is based upon tuple calculus. It uses basic block constructs to express the queries in the form select from where. Select clause mentions the attribute being projected, from clause mentions the relations needed to query, and where clause specifies the selection as well as the join condition. SQL syntax is expanded further to accommodate other operations. Another language which is based on tuple calculus is Quel, QEL, which actually uses the range variables as in tuple calculus. Its syntax includes range of, is, then it uses retrieve and where. This language was proposed in the relational DBMS Ingress. The system is currently still supported by Computer Associated, but Quel language is no longer there. Another variation of relational calculus domain is called the domain relational calculus, or simply domain calculus, is equivalent to tuple relational calculus and to relational algebra. The language called QBE, query by example, that is related to the domain calculus was developed almost concurrently by SQL at IBM Research. Yorktown Heights, New York. Domain calculus was thought as a way to explain what QBE does. Domain calculus differs from tuple calculus in the type of variables used in formulas. Rather than having variables range over tuples, the variables range over single values from domains of attributes. To form a relation of degrees n for a query result, we must have n of those domain variables, one for each attribute. An expression of the domain calculus is of the form where x sub 1 through m plus n are domain variables that range over domains of attributes. A condition or cond is a condition of or formula of the domain relational calculus. Here's an example of retrieval of the birthday and address of an employee whose name is John B. Smith. Abbreviated notation employee uses the variables without the separating commas between each of the column names. 10 variables for the employee relations are needed, one for the range of the domains of each variable, of each attribute in order. Of the 10 variables, only U and V are free. Specify the request attributes birthday address by the free domain variables U for BD and V for address. Specify the condition for selecting a tuple used following the bar, namely that the sequence of values assigned to the variables be a tuple of the employee relation and that the value for Q, F name, R, and S be John, B, and Smith, respectively. And with that, we've reached the end of our discussion of relational algebra and relational calculus. As always, if you have any questions, do let me know. That's what I'm here for. Stay safe, and we'll speak again soon.